Okay, let's have a look at an application from our circular motion work. And in this case, we're going to have a look at what happens to cars or other vehicles as they travel through flat horizontal turns. So our diagram here depicts our car travelling around. We've drawn a complete, well, it's not a circle, but it's a depiction of our revolution. This car is only going to go through some component of that complete revolution. So as the car travels through, it's going to be acted upon by a centripetal force that's acting toward the centre of this turn. And we're also going to have a radius r for the turn as the car travels through it. Slightly different diagram. We've got our radius here. This is a top-down diagram. Centripetal force acting through to the centre of that circle. And we have a velocity v that's tangential to this force. So if we were to put this car on a very low frictional surface with the road, we would find that this car slides off very easily. Question is, at what speed would it do it? To get to that stage, we need to go through and have a look at some of the other forces that are on this car. First of all, as this car is travelling around in this direction, we've got the force of gravity acting down through the car. We also have a normal force that's acting in an equal and opposite direction that's caused by the road acting on the car, where N is equal to our normal force. Now we also have this component which is our static frictional force that's holding this car in so that it doesn't slide off the road. Now there are no other forces on here, so we can say that this centripetal force is equal to this static force. So from there we can start to work through to finally look at what the maximum velocity or the maximum speed for this car would be given a certain frictional condition. So we say here that our centripetal force is equal to our static force. We can substitute in mv squared over r for our centripetal force. We can also substitute in our mu s, which is our coefficient of friction, our static coefficient of friction, times the normal force. We see here we've got m's on both sides, so we can get rid of those. So we get v squared is equal to mu s times acceleration due to gravity times our radius, and we take the square root of both sides. So the velocity at which we start to get slippage is equal to the square root of mu s times g times r. So let's look at how we apply this practically. And to do that, we're going to take a question like this one. Let's say a car takes a turn of radius 70 metres. The tyres on the road have a coefficient of friction of 0.7. We're asked, what is the maximum speed the car can travel before it slips off the road? So we've got our equation, v equals the square root of mu s times g times r. We've got our 0.7 for our mu s. We've got 9.8 for our acceleration due to gravity, 70 metres for our radius. If we put those numbers into our calculator, we get a maximum velocity of 22 metres per second squared before the car will start slipping, before it exceeds that slipping point. Now what happens if we reduce this coefficient of friction between the road and the car? Let's say we go from 0.7 to 0.2. Once again we go through the same process and we find that our maximum velocity before we get slippage has been reduced by half. So as that coefficient of friction decreases, we gradually get down to a point where we'll get slippage with virtually no speed at all. So the other interesting thing to note here is this velocity is independent of mass. So we could get a large car, a small car, a bicycle, whatever it is, it's independent of the mass of that vehicle and therefore is only dependent on the radius and the coefficient of friction.